Okay, this is the second recording on equilibrium. We are still on chapter 15. I will remind you again, this is the most important unit to pay very, very close attention, because everything we are learning now will be a background for chapter 16. So pay very close attention. Objectives: you will be able to calculate the reaction quotient, and by comparison with the value of Kc or Kp, determine whether a reaction is in equilibrium. If it is not at equilibrium, you should be able to predict in which direction it will shift to reach equilibrium. Your homework is the quest general and gas phase equilibrium 2. We already assigned O1. This is O2. I'm just telling you right now, the very last question is very challenging. Very challenging. And also for quest 01, there is a question that asks you for the equilibrium constant. There are ionic compounds in aqueous solution. You will need to write the net ionic equation to find the right answer. The net ionic equation. So anyone who comes here after school, not Mondays, after school, then you have question with those two, I will help you. Or during lunch. Okay, what does the value of K mean? If you have a K that is very large or very small, what does it mean? If you remember, K equal product over reactants. Concentration or pressure of products over reactants. Therefore, if K is greater than 1, that means you have more products at equilibrium than reactant. It makes sense. Alright? Because the numerator would be larger, that means you have more products than reactant. And then the language you need to use for that is products are favorable at equilibrium. You have more products than reactant. If K is less than 1, I need for you to imagine that quotient. It is products over reactants. This is your K. Therefore, if K is less than 1, that means the product is less than the reactant. You have more reactant at equilibrium. And the term you use is reactants are favored. Okay, get used to that language. If it's greater than 1, then you say products are favored. If it's less than 1, you say reactants are favored at equilibrium. Now, how can we manipulate the equilibrium constant? I need for you to listen carefully to this. This is the forward reaction. You have N2O4, equilibrium give you 2NO2. K equal the products NO2 squared over N2O4. Let's say, for example, K is 0.212. For the reverse reaction, now we have the products is the reactant. We reverse the reaction. K equal the products N2O4 over the reactants 2NO2. As you can see, this is the inverse of that one. In other words, if you flip an equation, the K for that reverse reaction is the inverse of the forward for K for the forward reaction. Let me repeat. If you have an equation, you reverse it. The K for that reverse reaction is the inverse of the K for the forward reaction. Okay, let's see if we have more. Now look at this. This is the forward reaction. K equal N2O NO2 squared over NO2. But what happened? If you take that equation, you double it. We have doubled that reactant, you have doubled the product. Now the K for that that doubled equation is NO2 to the fourth over N2O4 to the squared. If you look at your result, the K is squared. So what you need to learn from this, if you double an equation, you need to square the K. Double an equation, you square the K. Reverse that equation, the K will be the inverse. When you double an equation, your K will be the square. So if you can pull out your calculator right now, please, and then help me. Let's solve this problem. The following equilibrium concentrations were observed for the Haber process. I need for you to get used to this. Haber process is the formation of ammonia from nitrogen gas and hydrogen gas. Whenever they tell you the Haber process, it is that equation. Now, they did not even give me the equation. They say calculate the value of K at 127 degrees Celsius for this reaction. So, you should always start with a balanced chemical equation. And again, I want you to get used to that expression. Haber process is the formation of ammonia from nitrogen gas and hydrogen gas to produce ammonia. And a lot of people make a lot of money with this just by being able to manipulate that equilibrium. This is ammonia they use for fertilizer, and then you balance this equation. I have 2 ammonia and 3 H2. So get used to that balance equation. You will be using it a lot. They ask me for K, so I write down K, or I can write down KC. Remember last time I told you, you should always write the expression, because you have a full point for just writing the expression before you plug any number. And then we said last time, make sure you use square bracket, because it means concentration. So we have N2, concentration, molarity. This is your H2 cube. Therefore, and then you go to a next line, you write down your K, C equal, and then you plug the numbers. I have the concentration of ammonia, which is, let me create a little bit of more space here. All right, let's go with K equal. And then I just check here. Now that I'm using numbers, I don't use square bracket. I can use parentheses. The concentration of my ammonia is 3.1 times 10 to the negative 2, close parentheses, this is squared, over the concentration of nitrogen, which is 8.5, times 10 to the negative 1 to the first power, times the concentration of hydrogen, which is 3.1, times 10 to the negative 3. And then this is a cube. Therefore, K equal, can someone 37,000. I hope other people have tried, because it sounds very large to me. I always need people to all of you to try to make sure we have the right answer. What is it? 37,950. And we said you don't use unit for K. One question from Quest is they ask you, why don't you use unit? The unit just cancel out. You have the molarity everywhere cancel out. This is a question from Quest. So I need for you to remember that number, unless someone protest and tell me this is not right. So let's answer the next question. The question is calculate the value of the equilibrium constant at 127. They ask me for K again, but now they give me an equation. This is an equation they gave me. So I need for you to see exactly the difference between the equation I had before and the equation they gave me right now. It is just the inverse. It is a reverse. It is the inverse. Okay. Alright. So how do I find K? K equal. The equation is reverse. So how do we find K? It is the inverse of the original K. It is the inverse of the original K, which is 1 over, was it 37,950? So that K prime equal what? (2.64 times 10 to the negative 5). Negative 5. Alright, everybody try for me, please. So we won't carry mistakes throughout the video. So you see, this is the reverse reaction. So you need to get the inverse of your K. Let me reset again. Now they say calculate the value of the equilibrium constant at 127 degrees Celsius for the reaction given by the equation. I need for you to look at this equation and tell me exactly what they did to your original equation. Okay, if you look at carefully, the equation is cut in half. Cut in half. You can take your time and find K the long way, or you can do K, that K equal, what do I do with the original K? Square root it. It is the square root of the original K. You are right. It is the square root of, what is it, 37,950. So K equal 194.8. 194.8. No units. The units cancel out. Alright, so you can see how you can save time on the test. Some students would take their time and use this again, use the coefficient from that new balance equation to find K. But if you see it is the reverse of the original equation, you just get the inverse of K. If it's double, you get the square. If it's half, you get the square root of your K. Alright, the reaction quotient. We had discussed this before. Okay, let's review. The reaction quotient is the exact same thing as K, except it is at any other time that is not at equilibrium. Okay, Q gives the same ratio of the equilibrium expression, but a system is not at equilibrium. Any initial concentration, okay, or any other term that is not equilibrium. So you will be dealing with Q a lot. Now, and if I to look at this carefully, when K equal Q, the equation is at equilibrium. K equal Q, equilibrium. If Q is less than K, the reaction, now let me give you two easy tricks to remember where the equation will shift, because this is very important. Okay, so last time the trick I gave you, I said to write K and Q in alphabetical order. I said to write K, I said to write Q, and then compare K and Q. If Q is less than, so I need to put the greater than sign facing K. Greater than. And then that's the way my arrow from the equation will go. That's mean the equation will shift to the right, to the product side, to increase your K. Reaction forms products. The reaction will shift to the right to produce more product. Okay, if K, let me write down K again. This is Q. If Q is greater, if I put a greater sign facing Q, greater than K, this will be the head of the arrow. That means the reaction will shift to the left to produce more reactant. Okay, reaction for more reactant. This is the trick I gave you. Let me give you another one that is even easier. Okay, so let's reset this. So there should be no excuse. You don't know where it will shift. Now I need for you to think of a number line. This is number line. Okay, so you have your smallest number here, the largest one, and you have K. K is where you want to be. K is equilibrium. That's where you want to be. Okay, if Q is greater than K, that means it's on this side of the number line. You want to be at K. That means you need to go this way to get to K. Okay, if Q is greater than K, that means Q is right here. You want to be at K. So it will go this way to reach K. Alright, I hope you understand. So you should know how the equation will shift. Let's practice. Okay, be ready? Ready, calculator please. Calculator please, everybody please. The reaction quotient for the synthesis of ammonia. Here we go again. At 500 degrees Celsius, the equilibrium constant is. This is your K. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. That means all of those concentrations, they are concentrations that are not at equilibrium. They are at any other time except for equilibrium. That means I have to find Q for each one of them. So Q equal, so I have to write my balance equation for the system of ammonia. I need to write my equation. It is 3H2 plus N2 yield 2 ammonia, NH3. Okay, so let me write my expression for this is Q equal, this is my ammonia squared over H2 cube times N2, and then I just plug numbers. Q equal, all right, so it is 1.1. You already have the final, is that final answer? You have Q equal, is that right? Okay, Q equal, what is it? 12.5. Okay, 12.5 times 10 to the 6. Okay, how come you have 12.5? In scientific notation, 1.25 times 10 to the 7. Now, all you have to do is compare Q with K. Remember, okay? It is 6 times 10 to the negative 2. That means Q is, did you say 1.25 times 10 to the positive 7? So Q is greater than K. And remember, K is where you want to be. This is your K, this is Q. Therefore, the equation will shift to the left, not product, to the reactant. Now, let me tell you, I would advise you not to use left and right because you may get confused. Why don't we rather it will shift to the reactant side? Okay, because believe me, I'm not kidding. Some students forget their left and right when they use that expression. Okay, so make sure, you see, I'm left-handed, I have to look at that side to know if it's my left hand. So it's better to say shift to the reactant side, shift to the product side. Okay, when I mix my hand, now I don't know which is left, which is right. They are mixed. So you shift to the reactant side. Now, let's see how fast can we go. Let's see if someone can find Q for this example for me. Help me, because you know the time is always. This ammonia is 2 times 10 to the negative 4. N is 1.50 times 10 to the negative 5. Hydrogen is 3.54 times 10 to the negative 1. Negative 1. So can someone tell me Q for this example? Let's see how fast can we go. Let's see if I can find a joke to give you while you are doing the math. So we won't waste the time. Now, what I can tell you, not a joke, but remember K is temperature dependent. The only time K will change for a specific reaction is if you change the temperature. As long as the temperature is constant, K for that specific equation will always be that K. Once you change the temperature, you change K. So Q for this equation is 6 times 10 to the negative 2. Now, 6 times 10 to the negative 2. Will the equation shift to the left or to the right? No shift. No shift. Now, let's see how fast can you go right here for the last one. Alright. Q for letter C. Okay, let's see if I can tell you a joke while we are waiting for people to solve. Q for the last case. Okay, the joke is not coming. 2 times 10 to the negative 3. This is Q. Is Q greater or less than K? Less than K. If it's less than K, this is my K. That's where I want to be. Q is right here. Therefore, the equation will shift to the product side. It will shift to the product side. Alright. Le Chatelier's principle. Le Chatelier's principle. It looks like this is a good point for me to stop. Okay, so we already did 2 parts for equilibrium. I would advise you to keep up with me, because remember we will be in this unit for a while. Okay, so take care of yourself. I'll see you in class. Bye bye.